The Rocky Mountains, the backbone of North America. Rugged, spectacular, and majestic. Today, geologists are cracking open these rocks to expose their secrets. How did the remains of sea creatures end up in mountain peaks thousands of feet in the air? When did the Rockies form? Are they still rising today? And if they are, could the great forces that built the Rockies one day split North America in two? The Rockies, one of the greatest mountain chains on Earth. They stretch over 2,000 miles from the northern tip of British Columbia to the Rio Grande in New Mexico. Up to 300 miles wide, they form the Continental Divide, the Great Barrier between East and West. In Colorado alone, there are 58 mountain peaks over 14,000 feet tall. That's around 2.5 miles high. The Rockies were created by the most powerful geologic forces on Earth. Their dramatic story takes us on a journey from north to south through 200 million years of geological history. From their birthplace in Canada to the youngest peaks in the United States. It's a journey that takes us back into the Earth's ancient past. 200 million years ago, there were no Rockies. Even the continents looked different. There was just one giant landmass, Pangaea. But not for much longer. A vast rift is opening up, tearing this supercontinent apart. Over the next few million years, Pangaea will break apart into many smaller landmasses, eventually forming the present-day continent of North America. Earth's surface is broken up into vast pieces called plates. They sit on top of the Earth's warm, dense mantle. As the planet gradually cools, convection currents in the mantle slowly move these plates across the surface of the Earth. Where plates meet at their edges, there are often immense tectonic forces. These tensions can tear continents apart, but they also build mountains. Kirk Johnson, chief curator of the Denver Museum of Nature and Science, explains.
The action of continents crushing together or continents being hit by oceanic plates, those kinds of forces create basically planetary traffic accidents, and the wrecks result in mountains forming.
Evidence of the power of these immense forces can be found in one of the oldest and most northerly parts of the Rockies, Yoho National Park in British Columbia. Here, the fossils of thousands of peculiar prehistoric creatures lie in a cliff face near the peak of Mount Stephen, 8,000 feet above sea level. Geologist and mountain guide Paul McNeil specializes in the fossils of the Burgess Shale.
We see fossils here that we find almost nowhere else in the fossil record, and unlike any animal that's alive today.
This spiny creature is called Hallucigenia. And this bizarre specimen, Wiwaxia. These fossils offer clues to how the early northern Rockies formed, because they're not the remains of mountain-dwelling animals, but of sea creatures. They lived and died in a shallow tropical sea over 500 million years ago. The rocks that contain these extraordinary fossils formed on the sea floor.
Right around us, all of the rocks that we see used to be part of an ancient seabed. The limestones were part of the continental shelf, the shales were part of the deeper ocean waters, but it was all underwater.
Long before the Rockies formed, the west coast of North America was covered by a shallow sea. Over millions of years, clay, mud, and gravel settled on this coastal shelf, trapping and fossilizing tens of thousands of sea creatures. Layers of sediment solidified into rock up to 12 miles thick. The rock layers in this cliff are made from sediment laid down over 8,000 years. Today, these fossils are 1.5 miles above sea level. But once they were buried 6 miles under other layers of rock.
At their deepest point, these fossils were buried over 10 kilometers under the Earth's crust. And since then, they've been thrust up to over 2 kilometers up into the air, where we actually find them now.
This ancient rock formed offshore, 400 miles west of here. So what could have driven this ancient seafloor so far inland? And what pushed it up almost 8 miles? A force powerful enough to transform a flat ocean floor into massive mountains. Subduction. 180 million years ago, the North American plate was moving west, driven by the breakup of Pangaea, and the Pacific Ocean plate was heading east. The two colossal plates met head-on. In this clash of the titans, the denser Pacific Ocean plate was forced down beneath the more buoyant North American plate. Professor John Geisman from the University of New Mexico demonstrates.
What I'm going to do is simply tap on one of the sides, and I'm going to create an instability. Now we have oil starting to migrate, move its way over the top of the CD. Ah, voila, it's happening all by itself. I don't have to nudge it anymore. You see the oil moving its way across the CD like so, and the CD itself is going to begin to move like so into the oil, and the subduction process is completed. It's subducted into the interior of our planet, if you will. And it's a runaway process. You can't stop it.
On top of the subducting Pacific plate sat offshore islands. As the plate was pushed eastward, it carried these islands like a conveyor belt. One particularly large island reached the junction of the two plates and coast of North America, but it was too large and buoyant to be pushed down into the mantle. Instead, it slammed into the continental shelf on the western edge of the continent. The seabed was shoved eastward. It slowly folded up like a crumpled carpet. The fossils of the Burgess Shale were pushed thousands of feet into the air and miles inland. Geologist and author Ben Gadd has spent 30 years studying the Rockies here in British Columbia.
One way to imagine this whole pushing and shoving business is to do it on your hands. So you have the bony part of your hand, and then you have the skin over the top, right? So imagine that the bony part is the continental plate, and on top of that, you have all the sedimentary layers, right? That's the skin. So when the big push and shove comes, you have the skin being pushed along the bony layer, and as it gets pushed along, it wrinkles up. That's a good analogy for how the Rockies were formed. The older I get, the better this works for some reason.
Over millions of years, the plate collision forced up the northern Rockies. When the force of this collision lost its power, the first wave of mountain building came to an end. But that's not the end of the story. 80 million years after the first block of land hit the coast, a second one slammed into its back. It bulldozed everything eastward and upward. Layer after layer of rock was shoved higher and higher. First into hills, and then into mountains. gentle folds of rock evolved into the mighty Rockies. Today, these slabs of land, called terrains, make up British Columbia. As they continued to rise, the Rockies were continually sculpted by the momentous force of the elements. Even as they were pushed up, erosion was starting to tear them down. The Canadian Rockies. Jagged peaks, steep cliffs, and razor-sharp ridges, carved from the sedimentary rock of an ancient seabed. Despite being caught in a mighty plate collision and thrust up into towering peaks, the layers of rock in these mountains still lie almost horizontally. This provides a clue about how they rose up. As the blocks of land drove into the coast of North America, slabs of sedimentary rock were pressurized and folded so much that they snapped. Broken sheets of rock, up to a mile thick, shunted forwards and slid over each other again and again, in a process scientists call thrust faulting.
So the rock has actually been folded to the point where it can't be folded anymore. And at that point, the upper part of the fold will literally break and start sliding along. That's what we call a thrust fault. And it's a classic kind of fault for the Canadian Rockies.
Sedimentary rock forms when younger layers of sediment settle on top of older layers. But here in the Rockies, layers of different ages are jumbled up. Thrust faulting pushed older layers of sedimentary rock up and over younger layers.
Suppose that we think of this book as being a continuation of the layered rock that we see here. Now in a thrust fault, what happens is this part will break up and it will slide along like this, and it can go rather a long way until eventually it stops. So now we have layers that were down here pushed up over these layers. Old rock pushed up and over younger rock.
In this laboratory sandbox, the layers of colored sand represent layers of sedimentary rock. As the sand pushes eastward to the right, thrust faults form, one in front of the other. Thrust faulting pushes older rock layers above younger to create the distinctive sawtooth ranges of the northern Rockies. These mountains first emerged 140 million years ago. Thrust faulting first built the western ranges, and then crept eastward, forming a new range further inland. 120 million years ago, the main ranges appeared. And then even further east, the front ranges, 85 million years ago. Thrust faulting began to slow down until eventually, 50 million years ago, it stopped. At Mount Yamnuska, the mountains and the foothills meet. Beyond lie the flat plains of Alberta and Montana. Immense forces pushed an ancient seabed thousands of feet into the air. But a very different force sculpted it into these striking peaks. Erosion. Evidence of erosion's power is strewn all over the mountainside. Piles of broken shale and heaps of ash-colored sediment called scree.
Erosion has been at least as important as the mountain building itself. It's the mountain building process, the up-piling, that gives you the elevation to give you the height of the landscape, but then the landscape itself is carved downward differentially. So erosion is very important. It actually gives us the landscape we see.
Erosion is so powerful that it has scraped up to 2 miles of solid rock off the top of these mountain peaks. And the main force of erosion is water.
Water loosens material, sends it downhill. Water dissolves minerals. Water freezes and breaks up the rocks.
The northern Rockies are made of sedimentary rock like sandstone, shale, and limestone. Relatively soft and soluble, these are easy prey for erosion. And here in Canada, water's erosive power takes on a new dimension. In this cold climate, snowfall freezes and compacts to form enormous sheets of ice, glaciers. The glaciers here creep forward at 50 feet per year. On a geologic timescale, this is fast. Glaciers pick up and carry loose rocks and boulders, which scour and scratch the rock beneath them. Like giant ice cream scoops, glaciers gouge out distinctive U-shaped valleys. And when they melt, they leave behind deep gorges and steep-sided peaks. Erosion has worn down these rocks over millions of years. But the Rockies are fighting back. While erosion attacks their summits, deep below ground, the mountains are still growing. Look at the Rockies, and it's like seeing the tip of an iceberg. Mountains have roots, which can be 5 or 6 times deeper than their height. This mountain stands over 2 miles high, but its hidden root could extend 13 miles underground. These roots are the Rockies' secret defense against erosion. Structural geologist Carl Karlstrom from the University of New Mexico demonstrates using blocks of ice. The red and green ice layers represent the mountains above ground, and the white ice their roots below ground.
Mountains are not static things. The Earth's surface is continually being reshaped by erosion, by rivers, by glaciers that tear the mountains down. So let's imagine I'm eroding the mountains now, and I'll just pull one of the blocks off. The overall surface has gone down. The continent has gotten thinner, its roots come up, and now this rock, which was deep in the earth a minute ago, underneath the green layer, has come to the surface. That's called rock uplift. So I guess I'll erode off the pink layer too. We're back down to a continent without a major mountain belt, something like the eastern part of North America.
When the heavy weight of the mountain is eroded away, the root rebounds upward. This process means that the Rockies are constantly topped up from beneath. In Canada, thrust faulting and erosion have shaped the mountains. But as we travel south, this distinctive landscape is about to change. Just south of the US border in the state of Montana, a new rock appears among the Rockies: granite. This is the first clue that the mountains of the American Rockies are radically different. On our journey south along the Rocky Mountains, we're entering a very different landscape. From Montana southward, the Rockies are made from ancient granite, 1.7 billion years old. Granite makes up much of the deepest part of the continental crust. That's why geologists call this rock the basement. The Canadian Rockies are built from sedimentary rocks piled up on top of the continental foundations. So why does granite suddenly appear here in the American Rockies? But there's an even greater puzzle. Mountains usually form close to plate boundaries, but the southern Rockies sit a long way from the plate margin. The Front Range in Colorado is 1,000 miles from where the Pacific and North American plates actually meet. Geologists have come up with an explanation. They believe that the subducting Pacific Ocean plate is responsible. Ocean crust had been pushed deep into the mantle beneath North America for 100 million years when something unusual happened. 70 million years ago, the Pacific Ocean plate started to subduct at a shallower angle. Instead of plummeting steeply, it sliced beneath North America horizontally. This change had dramatic consequences.
The big oceanic plate in the Pacific didn't go deep down, it went in shallow like a spatula under a pizza. So something happened 68 million years ago over in California. That plate drives under North America, but instead of diving deeply, it comes in shallow, and 1,000 miles away from the coast, up from the ground, sprout the Rocky Mountains.
For millions of years, the ocean plate scraped along the underside of North America. It created friction, breaking up the basement granite of the North American plate and punching it upward. Structural geologist Carl Karlstrom demonstrates.
Because it was at a shallower angle beneath North America, it was scraping along the base of North America. When that happens, it puts the plate under compression like this, because it's being both pushed at the end and scraped along at the bottom. So it squeezes, pushes up the mountains, and it transferred this mountain building from the edge to great distance from the plate margin.
The shallow angle trajectory of the Pacific Ocean plate explains why these mountains formed so far inland. And it also explains the presence of granite. Thrust up through layers of sedimentary rock, the broken granite became the Rocky Mountains of the South. Red Rocks Park, Denver, Colorado. A landscape forged by granite uplift. Kirk Johnson demonstrates how these granite peaks punched up through the layers of red rock around them.
I'm going to use my assistants, Veronica and Ian, to help me explain how the Rocky Mountains in Colorado formed. Imagine, if you will, that Veronica and Ian are composed of 1.7 billion-year-old metamorphic rocks, the basement rock of Colorado.
Before the mountains grew, layers of sedimentary rock covered the granite.
And then about 68 million years ago, the mountain where Ian is starts to break and lift up and move up. So you see the uplift forming. And what's happening is that layer of sediments being deformed and bent. And these are the flat irons at Red Rocks. As the mountain comes up, overlying sediments are eroded off and deposited into the adjacent basin. And eventually, Ian's granitic back is exposed as the core of the Rocky Mountains. Veronica remains deeply buried beneath Denver, still covered with deep sediments, and the sediments eroded off the uplifting Rocky Mountains.
Johnson is investigating exactly when these events took place. He focuses on the Colorado Rockies Front Range, which runs 350 miles between North and South Colorado. Dating the Rockies requires real detective work. And like all detective work, you get clues by digging up dirt.
Yeah, so it's sort of counterintuitive. To understand mountains, you don't look at the mountains necessarily, you look at the debris from those mountains. So just like a detective would go through a criminal's garbage can, the basin adjacent to the mountain range is sort of a garbage can of the adjacent mountains. The mountain goes up, it sheds all its garbage off to the side, in this case sedimentary rock and fossils, volcanic ash beds, layers of lava. We can look at that garbage and reconstruct the chronology of the uplifting mountain range.
Today, this debris forms layers of sediment 10,000 feet thick beneath the city of Denver. In their mission to date these massive peaks, Johnson and his colleagues search for the tiniest clues, like fossilized leaves and pollen. For Doug Nichols from the Denver Museum of Nature and Science, these microscopic grains of pollen provide a valuable lead.
Pollen can be used to date the uplift of mountains because plants that were living at the time the mountains were coming up were shedding their pollen, which was becoming incorporated into sediment, which was being eroded from those same mountains. And I'm looking for the particular species of pollen that can tell me the age of the sample.
Each sample of sediment can contain thousands of fossilized pollen particles. Nichols examines a single grain. Every plant genus has distinctive shaped pollen. So by identifying the species of plant and its age, Nichols can start to date the exact uplift of Colorado's Rockies.
We pretty well understand that the uplift began 65 to 70 million years ago because we find distinctive kinds of pollen produced by plants that only lived 65 to 70 million years ago.
Sometime during this 5 million year period, Colorado's Rockies began to rise. But geologists can narrow this window even further, thanks to one of the most catastrophic events in history. Years ago, an asteroid smashed into the Earth. It wiped out the dinosaurs and left a distinctive line in the sediments by Colorado's Rocky Mountains. This pale yellow layer in the rock contains the remains of the huge asteroid. Because it's sandwiched between layers of debris that eroded off the Rockies, we know that the Rockies must have been up and eroding at the time of impact, 65.5 million years ago. Kirk Johnson specializes in dating fossilized leaves. He uses them to date the Rockies' birth even more precisely. Geologists know that 69 million years ago, Colorado was covered by a shallow sea. But Johnson's fossil leaves show that just a million years later, there were plants here. Johnson combines his findings with Nichols' pollen evidence to come up with a million-year window during which the Colorado Rockies must have emerged. And compared with the northern Rockies, these mountains grew up fast.
We know that 69 million years ago, Colorado was covered by a shallow sea. We know that at 68 million years ago, the Rocky Mountains were up. So sometime in that 1 million period, 1 million years, the Rocky Mountains came up. It may have taken all the 1 million years. It may have happened in 200,000 years. We don't know that yet, but we're working on that particular question.
Although Johnson's team can't yet say how quickly the mountains grew, they are certain of one thing. 68 million years ago, the American Rockies had arrived. As we continue south through the Rockies, the landscape evolves once again. 35 million years ago at the southern tip of the mountain chain, volcanoes appeared among the peaks, triggered by changes deep beneath America. A new explosive era had begun. As we travel south 2,000 miles through the Rockies and forward through their 200 million year history, we reach Albuquerque, New Mexico. Here, a dramatic change deep beneath America triggered the most explosive phase in the evolution of the Rockies. "70 million years ago, the subducting Pacific Ocean plate punched up huge blocks of basement granite, forming the Rockies of New Mexico. "35 million years later, the Pacific Ocean plate began to peel away from the underside of the North American continent. As the ocean plate sunk deeper, warm mantle came into contact with the underside of the North American plate, right underneath parts of the southern Rocky Mountains. Just as the burner on a hot air balloon makes the air less dense, causing the balloon to float upward through the cooler air around it, so warm, buoyant mantle rose up through the cooler, denser mantle beneath the mountains. Carl Karlstrom thinks that this caused the Rockies to grow even taller.
Well, let's think about uplift of mountains in the context of this analogy of a hot air balloon. We're floating high because we're more buoyant than the air around us. And if we want to go up, actually get still higher, we'll just turn on the burner and fire it up, and then the air becomes lighter within the balloon, causing a dynamic or an active uplift. And we can think of that in the context of mountains as if an upwelling of warm and buoyant mantle is actually pushing up the mountains.
But it's not just the mountains that were affected. The upwelling mantle also stretched the crust above. This sandbox simulation demonstrates the stretching process. As the continent pulled apart, the crust thinned and fractured. An immense crevice, called the Rio Grande Rift, opened up in the heart of the Rockies. In parts of the southern Rockies, the crust is over 30 miles thick, but in places beneath the rift, it's just 17 miles thick. This thin crust triggered something dramatic. Under immense pressure from rising heat in the mantle, it gave way. Red-hot magma blasted out onto the New Mexico landscape. And volcanoes punctured the Rio Grande Rift. Scientists believe that hot magma has surged up from the mantle many times over the past 35 million years. These surges led to renewed volcanism in the Rio Grande Rift. But this is not ancient history. The last eruption, just 1,500 years ago, flooded New Mexico with a river of molten lava 44 miles long. Could such recent eruptions mean that hot magma is ballooning beneath Earth's surface today? Could the Rockies of New Mexico still be on the rise? Laura Crossi, a geologist at the University of New Mexico, is on a mission to find out. Working with Carl Karlstrom, Crossi is focusing on a fault where the Rio Grande Rift meets the Rockies. Here, hot springs bubble up to the surface from deep below. Gases in the water can provide a clue to the activity in the mantle.
This point along this fault is a place where these fluids are finding their way to the surface because of the extension, the tectonic activity. We're able to come here and have a window into that deep, deep world, all the way to the mantle.
Beneath Earth's surface, gases are under immense pressure and dissolve in water. When they reach the surface, they escape as bubbles. Analyzing samples of the gas bubbles, Crossy discovers carbon dioxide and traces of helium-3. Carbon dioxide and helium-3 are both byproducts of activity in the mantle. Their presence indicates that deep beneath the surface, rock in the mantle is melting and on the move. Like a rising hot air balloon, hot, buoyant magma is slowly surging up beneath both the rift and the Rockies. This is evidence that here in New Mexico, the Rocky Mountains are far from dead. They could still be growing, thrust higher by rising mantle. Karlstrom believes that in the future, there will be a wider rift and taller, more spectacular Rockies.
I think portions of the Rocky Mountains are going up dynamically, and that they are getting higher, and the Rockies are getting higher, and certainly in the million-year time frame, we will have more interesting, higher, and more rugged mountains, I would predict.
Having investigated their past, geologists are now looking to their future, and it's bleak. The Rockies are doomed, and North America's destiny hangs in the balance. On this journey through the Rocky Mountains' 200-million-year history, we've witnessed their dramatic birth and examined their complex evolution. Now we turn to their uncertain future, a future that goes hand in hand with the fate of the whole North American continent. This is the Columbia Icefield in Alberta, Canada, where geologists are already seeing how the mountains are changing. Within 100 years, it could look something like this. Human activity is altering the course of geological history. Increasing global temperatures are taking their toll on the mountain's glaciers. They're melting. Brian Luckman from the University of Western Ontario wants to know how fast. During the winter, glaciers grow. An advancing glacier pushes a pile of eroded rubble ahead of itself, called a moraine. When the glacier shrinks back in summer, it leaves behind this pile of debris in its wake. It's a telltale sign that the glacier is melting away.
Because the glacier over time is retreating continuously, then what you have left are a series of these annual moraine ridges, which mark the furthest point of advance during the previous winter.
Luckman walks between the moraines, using GPS to map the distance between each one. The greater the distance between them, the faster the glacier is melting.
Glaciers are one of the most effective ways to demonstrate to people that the climate is changing. You've only got to come here twice or look at some of the older photographs to realize something radically is changing.
These two photographs of the 3.5-mile-long Athabasca Glacier show how far it has retreated over the past 30 years. And these photos of the Grinnell Glacier in Montana show that America's glaciers are disappearing as well. One day, the glaciers that have shaped these steep-sided peaks and U-shaped valleys will disappear. But water erosion will continue to sculpt these mountains, beating them down and softening their jagged edges.
The future of the Rockies is that they're eroding at the rate of about 0.06 of a millimeter per year. This is based on taking a sample of river water, measuring the sediment in it, and seeing how fast the Rockies are being carried off to the sea.
The relentless force of erosion has sealed the fate of the Rocky Mountains since they first began to rise. One day, they will erode away to nothing.
The Rockies that we see today, the beautiful mountains, why tourists come here, why it's just one of the most dramatic places on the earth, they're eroding away. And so if we look at all the rivers draining off of them, they're full of silt and sand, and that is our Rockies slowly bleeding to death.
The Rockies will eventually dissolve away. But far in the distant future, there could be a final devastating twist to their story. A continent ripped in two. The future of the Rocky Mountains is inevitable. Thanks to the relentless force of erosion, they will one day disappear. But they will leave a legacy. The Rio Grande Rift. A great tear in the Earth's crust that could one day split North America in two. Geologist Mizumi Roy and her colleague Nicholas George, both from the University of New Mexico, are taking part in an ambitious 5-year project. Its aim? To monitor the widening of the Rio Grande Rift. The team is setting up GPS stations along the length of the rift, like this one in remote New Mexico, 3 hours from Albuquerque. The GPS receivers are buried in the bedrock to a depth of around 5 feet. When the Earth moves, the receivers move too. Roy explains.
If you have 2 GPS stations, then you have information about relative motion along a line that connects the 2 stations.
A network of GPS stations allows the team to build up a much more detailed map of the rift's motions.
By looking at the difference between the coordinates between the GPS stations through time, we get a good idea of the relative motion between each of these stations.
The team has set up 24 GPS stations along the Rio Grande Rift. It's early days, but the team expects to find that the rift is widening between 0.5 and 2 millimeters every year. It's a very slow process. But little by little, the continent is being unzipped.
The Rio Grande Rift is a rift system that's causing a continent to split. And if this process continues for tens of millions of years, you could eventually rift the North American continent apart.
There's a lot of indications that there's some action happening. Maybe some more is in the future for the Rocky Mountains, and another few million years and there will be greater tales to tell of active tectonism further to the north, where this Rio Grande Rift is trying to work its way and crack the continent. I think it'll be unsuccessful in that attempt, but it's giving it a good show.
The story of the Rocky Mountains began with the birth of the North American continent. And it could end with its death. One day, the Rio Grande Rift may split a continent. North America might become East and West America. But all this is hundreds of millions of years into the uncertain future. Today, the iconic Rockies are in their prime. The mountains that divide a continent unite us all in admiration. Dramatic and resilient, they will remain the backbone of North America for millions of years to come.
A split second, the Big Bang, and the whole universe was born.
In the blink of an eye, literally, so much can happen that it would blow your mind.
How did we get here? And what is the universe made of?
The secret of creation, the secret of everything is locked in that first second.
Technology stands on the brink of revealing what happened in the most important second of all time. In the beginning, there is nothing. No matter, no energy, not even empty space, because space itself doesn't exist. No time passes, because there's no such thing as time. From nowhere appears a fireball smaller than an atom. 10 trillion times hotter than the core of the sun. Everything that will become the universe explodes from a point millions of times smaller than a pinprick. Time begins. In 1 second, the blueprint for the entire cosmos is written. How it happened is the biggest mystery of all. Professor Lawrence Krauss has devoted his career to studying the first second after the Big Bang.
If we want to really understand our place in the universe, we have to go back to the very beginning and understand how it all came together.
Looking back to the instant of creation is a new idea. The theory of the Big Bang is widely accepted, but the concept is less than a century old.
But one of the things we have to put in perspective is how recent our understanding of the universe is. 80 years ago, the conventional wisdom in science was that the universe was static and eternal, had been around forever.
But this changes in 1929. At California's Mount Wilson Observatory, Edwin Hubble studies the light from galaxies. He observes that the farther the galaxy, the longer the wavelength of light it emits. Light waves stretch the more they travel, and stretching changes their wavelength. The same principle applies to sound waves. As a train approaches, the whistle's pitch rises. When it passes, the pitch lowers. As the train recedes, each sound wave has to travel farther than the last to reach your ear. The sound waves stretch, lowering the pitch. Something similar happens with light waves. If a galaxy is moving away from us, its light waves stretch, becoming longer and redder. It's called red shifting.
When we look at visible light, there's red at one end of the spectrum and blue at the other. Red radiation is the long wavelength radiation of visible light, whereas blue radiation is the short wavelengths. And as we look at the universe, we see the radiation from distant stars literally stretching so that the light gets redder. And the farther away we look, the redder the light is.
Galaxies around us have shifted to this red light.
We look out in all directions at distant galaxies, they're all moving away from us.
Nearly all galaxies are receding at 1 million miles an hour. If galaxies are speeding away from each other, at some point, they must have all been together. The universe is expanding outward from a single point. It's the first evidence that the universe had a beginning. Hubble's findings lead to a radical concept: the Big Bang Theory. Scientists believe that in the first second after the Big Bang, the building blocks were created for every star and planet in the cosmos. To prove it, they first need a new way to tell time.
We are thinking of fractions of time smaller than we think about in any other area of human activity, and smaller fractions of time than a race car or a sprinter or anything else. And what we've learned is that more can happen in a fraction of a second, in a blink of an eye, than you can imagine. It would just blow your mind.
Hours, minutes, and seconds are the basis of modern life. But events after the Big Bang happen in fragments of time far smaller than a second. To analyze what happens, scientists use a new measure of time called Planck time. 1 Planck time equals 10 to the minus 43 seconds. That's a decimal point, 42 zeros, and then a 1. It's an unimaginably small amount of time. Yet in this first tiny beat of Planck time, something happens that shapes the next 13.7 billion years. Out of the fireball, the 4 fundamental forces of nature form. Those forces underpin everything around us. Gravity is the reason stars and planets form. It rules the moon and tides and keeps us on the ground. Electromagnetism lights our cities, connects our phones, and runs our computers. And the 2 nuclear forces, strong and weak, bind the particles that make up our bodies and power the furnace of our sun. We're here because in the first second after the Big Bang, the 4 forces are created. Without them, the universe would be a featureless fog of radiation.
If there were no forces, nothing would happen. There'd be no television. There'd be no sports. There'd be no love, no hate, no human tragedy, all the things that make life worth living.
But in the first beat of Planck time, the 4 forces are still rolled into a single superforce. Gravity, nuclear, and electromagnetic forces have not yet divided. Physicist Michio Kaku studies how the forces split apart.
I like to think of it as a crystal, a beautiful symmetrical crystal, all the forces unified in their elegant simplicity at the beginning of time.
As our cosmic clock takes one more tick of Planck time, the tiny fireball universe expands. The 4 forces start to break apart. It's like rapidly cooling a super hot crystal. Cracks form.
It began to shatter into 4 pieces. The first piece to break off was gravity. Then the nuclear forces began to split off. And finally, we have this fragmented jewel of what used to be the superforce.
Those 4 fragments are still at work. Gravity keeps Earth in orbit. Nuclear forces make sunshine. And electromagnetic radiation, the light that bathes our planet. We're just fractions of a second into our journey, and already the foundations of our world are forming. The fireball universe. Still smaller than an atom, and 1,000 trillion degrees. To discover how the universe expands, scientists use telescopes so powerful they can see the past. When astrophysicist David Spergel looks up, he sees history.
As we look out in space, we look back in time. Light travels at a finite speed. So the light we see from the sun takes about 8 minutes to get here. We see the sun not as it is, but as it was 8 minutes ago. We look out the night sky, we see the nearby stars. They might be 10 or 20 light years away. We see them as they were 10 or 20 years ago.
The Big Bang was so powerful and so hot, remnants of that heat still survive. The heat began as super-hot X-ray radiation. As it stretched and cooled, it became visible light, shifting from blue to red, then becoming microwaves, and finally radio waves. This faint radiation shines down on Earth all the time. It's called Cosmic Microwave Background Radiation, or CMB.
The cosmic microwave background is the echo of creation itself. It's the embers, the afterglow of the original shock wave that created the universe. If we had microwave eyes that could see microwave radiation, then every night we would see the Big Bang coming out. Looking at the heavens, we would actually see an explosion.
More than 13 billion years later, we have a way to see this cosmic glow with the naked eye.
You take your TV set, switch it between channels. A couple percent of the static that you see on your TV screen is radiation from the Big Bang.
This cosmic radiation is a direct connection to the Big Bang. It also reveals the universe entered a new phase, less than a trillionth of a second after its creation. Cosmic radiation is the key to discovering what happens next. A few beats of Planck time tick by on our cosmic clock, and the fireball universe is transformed. One instant, the universe is billions of times smaller than an atom. The next, it inflates to the size of a baseball, growing more in this moment than in all the 13.7 billion years to come. Scientists call this rapid expansion inflation. And the evidence survives in the cosmic radiation left over from the Big Bang. Like static on your television, this cosmic radiation seems so constant and so even, it presents scientists with a puzzle.
When we measure the cosmic microwave background in that direction, its temperature is identical to its temperature in that direction. It's the same everywhere.
The only explanation is the universe inflates countless times faster than the speed of light. Inflation expands the fireball universe evenly, like a balloon blowing up, with a phenomenal breath of energy.
I try to imagine compressing a spring. I push it closer and closer and closer together so it's smaller and smaller and smaller, and I've stored a tremendous amount of energy in that spring, and when I let it go, it bursts out. And that stored energy drove an exponential expansion of space.
But if the entire universe is uniform from the first second after the Big Bang onward, how did the galaxies form? Planets and stars begin as clusters of particles. Over time, these particles of matter clump together under the force of gravity to form a dense mass. Earth began as a ball of particles that clumped together through friction and gravity. The sun that sustains life on Earth started out as a cloud of gas and dust. How did these clusters form in the first place? The early universe should be lumpy, not even. To link the formation of stars and planets all the way back to the first second after the Big Bang, NASA scientists like David Spergel developed the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite mission to measure the temperature of cosmic radiation in more detail than ever before.
While this radiation is everywhere, it's very faint. And to observe it in great detail across the whole sky, you want to get away from the Earth and any interfering sources of radiation.
7, igniters armed, green board, 5, 4...
NASA launches the probe in 2001.
Main engine start and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
It could produce the best ever snapshot of the universe in its first second.
The launch was incredibly exciting, tense, but exciting moment to see it go up and then realize it was working.
WMAP sits 1 million miles from Earth. It's so sensitive, it can measure the temperature of cosmic radiation within 1/millionth of a degree. For 5 years, WMAP analyzes the sky in minute detail.
It sits there with the Earth and Sun always behind it, staring out into space. The satellite's spinning very rapidly, It covers about a third of the sky every hour, spinning and making maps of the leftover radiation.
WMAP tracks the Earth as it orbits the Sun and scans the temperature of the whole sky. It generates detailed temperature maps like this one, and it reveals something remarkable. The blue and red patches on this map of the entire sky are tiny ripples in temperature.
The little blue regions represent regions that are a few tens of thousands of degrees colder. Red regions are a little bit hotter, so you're seeing tiny variations in temperature across the sky.
WMAP looks back over 13 billion years. As the universe evolves, these tiny ripples develop into clusters of particles that get bigger and bigger under the force of gravity, becoming just dense enough to trigger stars and galaxies to form.
I mean, it really was what I think we all dream of when we go into science. Looking at things that no one's looked at before, learning really exciting things about fundamental questions. Questions like, what's the universe made of? What happened in its first moments?
This is a map of how the universe looked in the first second after the Big Bang. The template for today's vast cosmos.
When the picture of the cosmic microwave background radiation first came out, the press said, "Ah, the face of God." Well, let's be real. It's not the face of God. What it really is a baby picture of the infant universe. So the discovery of the cosmic microwave background radiation ranks as one of the greatest discoveries in all of science.
Less than a trillionth of a second after the Big Bang, the fireball universe rapidly expands. Now an ultra-hot globe big enough to sit in the palm of your hand, the universe is seething with energy and radiation. But as the palm-sized universe expands and cools, something new starts to form. Only a fraction of a second after the Big Bang, and the destiny of the universe is already mapped out. The sun burns because of forces forged more than 13 billion years ago. The stars and planets form from the way the universe rapidly expands. Science can trace everything we see today back to the first second of creation. But we're here because of what happens in the next few beats of Planck time. The universe is flooded with the building blocks of matter. So far on our cosmic clock, the early universe is nothing but energy. How did pure energy turn into matter? Everything around you is made of matter. What you're sitting on, the air you breathe, the whole planet is made of matter, and matter is made of atoms. And in the first second after the Big Bang, the ingredients for atoms are created. How matter appeared mystified scientists until 1905, when Albert Einstein comes up with our most famous equation. E equals mc squared. Einstein's equation tells us that energy, E, and mass, m, are different forms of the same thing. Matter and energy are interchangeable. Some scientists later used this equation to create the most destructive weapon in history, the atomic bomb. It offers a clue to what happened in the first second. In a nuclear explosion, particles of matter are ripped apart to produce an enormous amount of energy. During the Big Bang, the exact opposite happens. An enormous amount of energy turns into matter. Einstein's equation prompts a conclusion. As the baby universe expands and cools, the pure energy of the Big Bang converts into the particles of matter that make us. We're only a fragment of a second into our journey. The first particles of matter appear. The universe is 1,000,000 times hotter than at the core of the sun, still far too hot for particles of matter to bond and form atoms. Scientists face a puzzle. What is this early state of matter like? And how does it become the protons and neutrons that form every atom in the universe?
Atoms were impossible. Think of putting an ice cube in a steam bath. The ice cube would melt immediately. You cannot have ice cubes in a steam bath.
You can see the proof in a block of ice. When water is cold enough, it's a solid. Warm it, and you get a liquid. Heat liquid water, and it boils away into a gas, water vapor. Superheat the gas, and the energy pumped in rips the atoms apart. Likewise, the universe in the first second is so hot, only the building blocks of atoms can exist.
If you were to journey into the early seconds of the universe, literally you would disintegrate. You would literally fall apart, and even the debris, the nuclei of your bodies, they too would fly apart into subatomic particles. There would be nothing left of your body.
There's only one way to see these super hot building blocks of matter in the first second after the Big Bang. Scientists must recreate conditions of the Big Bang itself.
The inside of a star is measured in tens of millions of degrees, but the Big Bang was measured in trillions upon trillions of degrees, so we have no way to simulate the instant of creation other than with a particle accelerator. By slamming protons into other protons, we can create temperatures not seen since the beginning of the universe itself. So particle accelerators are the only game in town when you talk about simulating Genesis.
This is Brookhaven National Laboratory in Long Island, home to the Relativistic Heavy Ion Collider, or RHIC, a 2.5-mile ring designed to smash the nuclei of gold atoms at nearly the speed of light.
With the particle accelerator, you slam subatomic particles together. As a consequence, we get a tremendous shower of debris, and then we want to make sense out of it. We want to know what's inside that collision.
The energy of the collision is colossal. On a small scale, it reproduces the embryonic universe in the first second. How? By ripping nuclei into the protons and neutrons they're made from. The energy is even enough to rip the protons and neutrons apart. Inside, scientists discover the building blocks of matter, tiny particles called quarks. But they're so small and move so fast, they're hard to track. If scientists can figure out how quarks behave, they'll unlock the secret of matter itself. What they find could revolutionize medicine and relaunch the space program. The project starts in 2000. Colliding nuclei creates a chaotic spray of particles. It takes 5 years to analyze the data. The results come in 2005. They're shocking.
We were expecting to find a gas when we slam gold nuclei into each other. So the shock was, it wasn't a gas at all. We found that it's more like a liquid. So this came quite a shock, because now when we begin to simulate the early universe, we have to get rid of this mental picture of a gas of subatomic particles. Now we know it's more like a liquid, literally like a soup.
When matter first appears in the universe, the quarks are so dense and so energized that the entire universe is like a liquid. the universe went from a glowing ball of energy to quark soup in less than a blink of an eye. The liquid universe is hot, dense, and violent, flooded with tiny particles in constant vigorous interaction. As our cosmic clock reaches a millionth of a second, the universe continues to expand and cool. It grows from the size of a baseball to the size of our solar system. Matter has materialized from pure energy. Without matter, none of us would be here. And in that first second, that very nearly happens. Something comes close to destroying all matter in the universe. Armageddon is brewing. A split second after the Big Bang, and the universe is flooded with the building blocks of atoms. These tiny particles of matter must survive in a battleground. Everything around us is made of matter formed from the energy released by the Big Bang. Every molecule, every atom, every quark. How we end up with a universe that consists of so much matter is one of our biggest questions. The particle accelerator may reveal the answer. When the first second is recreated, two types of matter are produced in equal parts. One is the type of matter we see around us. The other is its opposite, antimatter. Dr. Tara Shears explains they're two sides of the same coin.
This apple is made of matter. We know that every matter particle in the universe has an antimatter partner that was created in the Big Bang. Now, antimatter looks similar to normal matter, but not quite. In fact, it looks like the mirror reflection of matter. So an anti-apple looks like this.
If the universe was made of antimatter, it would essentially look identical to how it looks today. You and I would be made of antimatter, and anti-lovers would sit in anti-cars looking up at an anti-moon at night making anti-love, and it would be largely the same.
But matter and antimatter are mortal enemies. They can't coexist.
When we have a matter particle meeting an antimatter particle of the same type, then they annihilate, they explode together, they destroy each other. All the energy that the matter and antimatter particle have goes into one large explosion of huge, tremendous energy.
Fractions of a second after the Big Bang and the future of the universe is at stake, matter and antimatter are locked in a battle to the death. A millionth of a second after the Big Bang, and a battle rages. When matter and antimatter clash, the result is explosive. Just one apple-sized clump of matter hitting its antimatter equivalent would release as much energy as a 10-megaton nuclear bomb.
If you could go back to the really early universe just after the Big Bang, you'd find yourself in this seething mass of matter and antimatter annihilating each other. You'd find yourself in the middle of this cosmic battle between both sides, caught in the crossfire, if you like.
With all the particles in a super-dense liquid state, matter and antimatter quickly meet and destroy each other. Since they're created in equal numbers, and every matter particle that hits an antiparticle is annihilated, all matter should be destroyed as soon as it's created.
All the matter would have eventually found the antimatter and they would have annihilated, producing pure radiation. And we'd now have a universe. I was going to say we'd now be living in a universe of pure radiation, but we wouldn't be living in such a universe because we wouldn't be here. There'd be nothing but radiation.
But the universe is full of matter. How did it defeat antimatter? It's one of science's great mysteries. One theory is that antimatter is less stable and decays more quickly, creating a tiny imbalance between matter and antimatter. This tiny imbalance eventually allows matter to overwhelm antimatter. Whatever the truth, something happens just after the Big Bang that tips the balance in favor of matter.
And the whole battle stopped at that point, and what was left was a very small amount of matter. And it's that small amount of matter that makes the universe that we live in now. That means that we're the leftovers of this battle. We're the dregs. We're what's left when everybody else had finished.
The dregs go on to form everything around us. From the ground beneath our feet to the most distant galaxy. As the cosmic clock nears the end of the first second, nature's four forces have split off from the single superforce. The winner of the matter and antimatter war has been decided, and the subtle ripples in temperature that stretch across the universe mean that over the next billion years, gravity gathers clumps of matter to form galaxies. But one mystery remains, and it's a big one. We know how the building blocks of matter form, but we don't know what gives everything in the universe substance. We know so much about the first second, but a piece of the puzzle is missing. What gives everything in the universe mass? Mass makes it tough to get something moving, and makes it hard to stop. When we're pulled down to Earth, gravity is acting on our mass. On the Moon, gravity is weaker, so astronauts move slower, but their mass is the same as back on Earth. Even if an object weighs nothing, it still has mass. Something must have been created in the first second to give particles mass, but scientists haven't found it.
We have this hole. We have this missing piece. The centerpiece of this whole picture is what happened during that first second of creation. If you know that, then you can, quote, read the mind of God, as Albert Einstein used to say.
Mass is the very backbone of life.
If there were no mass, the universe would consist entirely of radiation, and nothing could bind together to form objects like you or I, or any of the things that appears to make the universe interesting. It would be a diffuse universe full of radiation, but very, very boring.
Discover how mass develops in the first second, and you uncover the root of life. If scientists can't find what gives particles their mass, that first second will remain an enigma. Our journey is almost finished, but a piece of the puzzle is missing, and it stumped scientists for decades. Then in 1964, at Britain's University of Edinburgh, physicist Peter Higgs comes up with a groundbreaking theory. He suggests an invisible force field sweeps across the universe in the first second, giving particles their mass. It's become known as the Higgs field. When particles interact with it, they gain mass.
For example, if I take a car and that's run out of gas and I push it on the road, eventually I can push it and I can move it along. But if it runs into the mud, if I try and push it, it will suddenly seem heavier. I can't push it as hard. It'll act as if it's heavier. Well, we think that particles have mass for a similar reason. There's this Higgs field, and some particles interact with it more strongly than others. And the particles that interact with it less strongly are easier to push, and therefore behave as if they're lighter. The particles that interact with it more strongly are harder to move and act as if they're heavier.
Like mud, the Higgs field sticks to everything. When particles enter the field, they gain mass. The more contact with the field, the more mass they gain. Scientists believe the Higgs field is carried by its own special particle, Journalists call it the God particle. Scientists call it the Higgs boson. They think identifying this particle could reveal how we got here. The math is good, but no particle accelerator was powerful enough to find the Higgs boson. Until now. Deep beneath the countryside in Geneva, Switzerland, is mankind's most expensive experiment, the Large Hadron Collider, or LHC. The world's biggest particle accelerator and the best shot at finding the missing Higgs.
We've got to see if the Higgs particle really exists. And that's why we have to build these mammoth accelerators to see if we can understand the mechanism responsible for the existence of everything we think of as solid and heavy in the universe today.
It cost $10 billion, took 14 years to build, and involves the work of 7,000 scientists. This year, they switch it on. On a small scale, it will recreate conditions last seen over 13.7 billion years ago. An explosion so powerful, it will echo the Big Bang itself. If it works, scientists like David Evans could solve the last mysteries of matter.
Because we're pushing the frontiers of science, we have to also push the frontiers of technology. It is, as well as probably the biggest machine in the world, it is certainly the most complex machine in the world.
Over 300 feet underground runs a 16-mile circular pipe. Inside, two beams of protons, thinner than a human hair, are accelerated to almost the speed of light, 186,000 miles per second. The LHC will smash particles together 7 times harder than any other accelerator. 300 trillion protons fly around the pipe in opposite directions and collide in the heart of enormous detectors. Lawrence Krauss inspects one of these detectors, each the size of a 5-story building.
Here we are at what's been aptly described as being one of the Gothic cathedrals of the 21st century. This monstrous structure made of thousands of tons of steel, more iron than in the Eiffel Tower, with tens of thousands of miles of wire. All of this designed by thousands of physicists from hundreds of countries, speaking dozens of different languages, with the precision of perhaps a millionth of an inch, just to detect what happens inside there.
The LHC uses 4 of these giant detectors along the beam pipe. The one they hope will find the Higgs is called Atlas. Atlas is half the length of a football field and weighs as much as a nuclear sub. It can detect 1 billion collisions per second. When the protons collide, the impact is so titanic, in a split second, it will recreate matter as it was just after the Big Bang. A shower of fundamental particles, like quarks. Somewhere in the debris, they hope to find the elusive Higgs. But finding one particle in this firestorm is like finding a speck of gold on a beach. The Higgs is so tiny and so short-lived, the detector won't see it directly. Instead, they hope to capture the trail it leaves behind, using the most high-tech cameras in the world.
When you look at a Skyrider, you see this gigantic plume of smoke, but where's the airplane? You never see the airplane. The airplane is too small to be seen. That's how we use detectors. Detectors cannot pick up the particle itself, but it can pick up the trail left over by the subatomic particle, and looking at the trail, we can determine what kind of particle it was and how fast it was moving.
The LHC will generate more data than any other instrument on the planet.
In a single second, the amount of information that's coming out of the collisions at the LHC that will be handled by these detectors is greater than the amount of information in all the libraries in all the countries in the world.
That data may hold the secret of mass, the missing piece in the universe's first second, and the doorway to the science of the future. To process all this information, the LHC uses the world's largest network of supercomputers. Even so, the search may take years to complete, but it's worth the wait. If it succeeds, the LHC could launch a new era in science. If it fails to find the Higgs and reveal how matter gets its mass, it will leave a hole in the riddle of the first second. New theories will have to be written, and more powerful experiments built.
Hey, I'm a realist. I realize that perhaps we'll find nothing. That could create a crisis in physics. It could stagnate all of physics if all of a sudden our machines are not powerful enough to unveil the next act, the next curtain, where we look at the next stage of matter and energy.
One thing they know, the LHC will take scientists closer to the Big Bang than ever before. It will reach back 13.7 billion years to recreate the very first second of the universe, the greatest second. Our cosmic clock takes its final beat of Planck time. The universe is 1 full second old. It's about 1,000 times the size of our solar system and flooded with particles of matter, the raw material of everything around us. The universe is cool enough for the sea of quarks to bunch in threes, forming protons and neutrons. In the saga of the universe, this first chapter set the course of history.
The first second of the universe was an incredibly exciting and important time. During that first second, all the matter in the universe was made. All of the neutrons and protons were made. All the key components to make the universe today, we think were already in place. And then everything just evolved forward.
In the next few minutes, the universe cools enough for protons and neutrons to form the first atomic nucleus. 300,000 years later appears the first atom. In hundreds of millions of years, matter clumps to form the first stars. And in 1 billion years, galaxies like the Milky Way. More than 9 billion years after the Big Bang, Earth is born. One Big Bang, one single second. The genesis of everything.
By the time you've got to the end of 1 second, the rest of cosmic history is prescribed, including, ultimately, the future of the universe.
More than 12 billion years after the Big Bang, humans evolve. A species with the intellect to ask, how did we get here? And what is the universe made of? This year, science moves closer to discovering the answer. And the secret will lie in the first epic second. Of all the
area that we're in, this groove was obviously gouged out by some force.
John Menzies has come to Mohawk Bay on the shores of Lake Erie to find out. The answer lies hidden in these cliffs. They look like mud, but they're ancient rock sediment. This was once solid bedrock. It was crushed by the Laurentide ice sheet and deposited here.
Based on the evidence that we're trying to sample here today, we hope that this will illustrate how the Great Lakes basins were formed and developed.
These tiny rock particles hold a secret. Menzies sets the sample in resin and slices it into thin sections. Normally, glacial erosion produces rock grains with jagged edges. These grains are nearly round.
If you look at this particular thin section, you can see this particular piece of rock, and you can see around it the effects of rotation, kind of indicative of the sediment being moved underneath the ice sheet and rolling and rotating beneath the ice. So in other words, the sediment has been tumbled and moved and rotated and sheared time and time again.
But how can a glacier produce both jagged and smooth rock grains? The explanation? Some of the ice inside the Laurentide Glacier moves faster than other areas of ice. The fast-moving ice is called an ice stream. Ice streams are like rivers of supercooled water. Water that's well below freezing, but doesn't solidify. These rivers can flow up to 3,000 feet a year, 10 times faster than the surrounding slow solid ice. Working 10 times faster, they can potentially dig 10 times deeper. More proof that the Laurentide contained fast ice lies beside Lake Ontario. This is an aerial photograph of the shoreline. It shows strange elongated hills. These are lumps of sediment called drumlins. As the glacier retreated, they were left behind. Here's how they formed.
So if we produce a blob of toothpaste, and this we take as the base of the ice, and so as the ice deforms, so does the toothpaste deform, and we produce this nice linear. You can actually see the small lineations, drumlin-like, streamlined forms that are actually being produced simply by moving one interface over another interface.
Just as fast ice leaves a trail of long, thin drumlins, it also tends to carve out long, thin lake basins. If fast ice alone carved the Great Lakes, it could have taken as little as 100,000 years. The ancient ice sheet gouged out millions of tons of rock, ground it into fine sediment, carried it away by meltwater, and flushed it out into the Atlantic Ocean. Left behind 5 enormous basins. The deepest, Lake Superior, more than 1,300 feet. The Great Lakes. But when did the enormous Laurentide Glacier melt and the basins fill with life-giving fresh water? Francine McCarthy holds a clue, a 12-foot tube of mud called a sediment core. The sample was taken from the bottom of Willoughby Bog, a swamp between Lakes Erie and Ontario.
This keeps a very good record of what went on when people weren't here to keep the history.
The core is made up of mud, pollen grains, and sediment deposited in the water when the lakes formed.
We remove material for radiocarbon dating, and the dates are about 1,700 years ago here, about 7,500 years ago here, and about 9,000 years ago near the base.
The cores reveal water was present at least 9,000 years ago. But beneath the 9,000-year-old layer is one even older. It's the last layer before hitting bedrock, so it must be the first layer deposited in the water. If McCarthy can date it, she can pinpoint when fresh water arrived and reveal the age of the lakes. But to date the layer, she needs organic material.
You can see the color contrast between the very inorganic and the bog material. This is impossible to date using radiocarbon dating, conventional radiocarbon dating techniques, because you can see that there's very little organic material here.
Just rock and clay, a dead end. But why are the early lakes lifeless? To find out what the early Great Lakes looked like, we need to return to Iceland and the Vatnajökull Glacier. Here at the base of the glacier is a newly born lake. Its basin was carved by ice and filled with meltwater. This is how the Great Lakes looked tens of thousands of years ago. And like the early lakes, this place is dead.
There was virtually no life in these proglacial lakes. It's very cold, it's a very harsh environment, there's very little light, so your whole ecosystem is unable to really get kick-started.
The reason? The water's strange milky color. These lakes are loaded with ground-up bedrock, sediment washed down from the glacier. This sediment blocks out light, and without light, small organisms like algae can't survive. No plants, no food, no life. As the Vatnajökull Glacier continues to melt, more water will flood this lake and dilute the sediment. Eventually, it will settle on the bottom, just as it did over thousands of years ago in the Great Lakes. This is the pale gray layer McCarthy discovered. The mystery remains. Scientists have to find some other way to date the age of the lakes. The answer could lie hidden in one of North America's most spectacular geological formations, Niagara Falls. Niagara is the mightiest waterfall in North America, and one of the Great Lakes' most awesome features. On average, 150,000 gallons pour over every minute, enough to fill over 60 Olympic-sized swimming pools. Niagara holds the answer to a prehistoric mystery. When did the ice retreat and the Great Lakes fill with water? John Menzies has come to investigate. It's the first time he's gotten this close to the falls.
It's just utterly incredible. You see the volume of water that's coming over per second. All the water from the central part of North America is flowing right over here as we stand. Fantastic.
It's possible to date the arrival of the water in the lakes because Niagara behaves very strangely. The falls are moving. Every year, they take one step back, 12 full inches toward Lake Erie. The reason for this movement is the rock. The falls are built on 2 layers of rock. At the top of the falls is a hard layer of limestone, known as cap rock. Underneath is a softer layer.
This is a piece of Queenston shale, which is the weaker rock from underneath the cap rock for this area of regional geology. And in fact, it's very, very easily to break, as you can see. Bingo.
The weak shale at the base of the falls is relentlessly pounded at up to 70 miles per hour. The constant hammering erodes the shale below and undermines the cap rock above.
The cap rock gets left like a cantilever effect, and then it simply breaks off, and it breaks off every so often, fairly dramatically. In fact, if we look at the falls, there's a huge rock that's actually fallen off in the last 100 years. In a sense, you can look at Niagara Falls as being, if you like, an ongoing process of destruction. Perpetual destruction, perpetual change.
The destruction means that the falls act like a giant timepiece, an enormous clock that allows geologists to date the age of Niagara and the lakes themselves. Until 100 years ago, the falls eroded 3 to 4 feet a year. As water was diverted for hydroelectric power, the erosion rate has fallen. But the falls are still eroding roughly ½ an inch a month.
Eventually, given time, the hotels, the casinos and so forth are going to be left behind in the track of the falls as the falls retreats to the south and leaves this touristic area in isolation.
If the falls continue to erode at this rate, in about 50,000 years, the falls will reach the base of Lake Erie itself. As the falls retreat, they carve a giant canyon, the Niagara Gorge. 3 miles downstream from Niagara, geologist Francine McCarthy can date the Great Lakes by searching for the fall's birthplace. The secret is hidden not in rocks, but in clamshells.
Well, that's perfect. We can identify that to species. It's definitely the kind of thing we want to radiocarbon date back at the lab.
This species of mollusk lives in Lake Erie. It was carried downriver and over the falls. The surging water wedged the mollusk into cracks at the base, where it died. The falls moved on. The shell remained. By carbon dating shells like this, McCarthy can prove Niagara Falls roared over this exact spot 7,000 years ago.
The water level would have had to have covered this area in order to deposit the little aquatic clams in the crannies where we find them.
Further proof can be seen in the strange rocks scattered around this whole area. These holes were cut into the rock by the constant pounding of water over the falls. But this isn't Niagara's birthplace. The further McCarthy walks from the falls, the further back in time she travels, and the older the shells she discovers. By analyzing shells found all along the gorge, McCarthy reveals the life cycle of the lakes. From Niagara's spectacular location today to their location in 1678, when the first written account was made. Downstream to the Whirlpool Rapids, 5,500 years ago. Through Niagara Glen, where McCarthy's shells reveal their location 7,000 years ago. To Queenston, 10,500 years ago. And finally, 7 miles downriver from the falls, where a natural ridge called the Niagara Escarpment cuts across the land. Scientists discover the oldest shells yet.
The Niagara Falls are 12,600 years old. They've been operating since water started melting from the Laurentide ice sheet.
And if Niagara Falls is 12,600 years old, then the Laurentide Glacier must have retreated at least 12,600 years ago, exposing the 2 lower lakes, Erie and Michigan. The mystery is solved. Like Niagara, the Great Lakes have continued to evolve over the millennia. But some changes happened much more dramatically than anyone imagined. Today, rainfall on Lake Superior takes 204 years to travel through all the other lakes before it reaches the Atlantic Ocean, more than 2,000 miles away. The Great Lakes flow east and always have, or so geologists thought. Scientists studying fossils in the Gulf of Mexico uncover surprising species. It forces them to reevaluate what they thought about the Great Lakes. Scientists analyzing 14,000-year-old shells discover the water in the Gulf of Mexico must have been less salty than today. But why? Only one source of fresh water was vast enough to dilute the Gulf: the Laurentide Glacier. Fossil records suggest the meltwater drained south along the Mississippi River to the Gulf. But then, Nearly 13,000 years ago, some titanic force diverted the flow from south to east. The question is, what force was powerful enough to divert the Great Lakes? 13,000 years ago, some unknown force diverted the flow of meltwater from the Laurentide Glacier. Geologist Alan West searches for answers on the shore of Lake Michigan.
This is a visual line that's actually where our greatest interest lies. The Great Lakes really began right at this line in the sediment.
West finds tiny specks the size of sesame seeds. They're made of carbon. West believes they're all that remains of a vast forest, incinerated at sizzling temperatures. But the most important clue lies inside each grain, a dazzling secret.
These small black dots, they're almost pure carbon, and when we check them with an electron microscope, we find that they contain millions and millions of diamonds.
Each diamond is 1,000 times smaller than a pinhead.